You're lying on a grassy hill on a cool night, the sky overhead a velvet blanket sprinkled with countless tiny lights. You point at one of those glittering specks and wonder, what exactly is a star? It's a question that has tugged at human curiosity since we first lifted our eyes to the heavens. And the answer is far more dramatic, bizarre, and, let's be honest, hilariously extreme than any sci-fi movie could ever conjure. Because we're about to embark on a cosmic journey that will take us from the fiery furnaces of newborn suns to the ghostly remnants of dead stars, all while slipping in a few jokes to keep our brains from overheating like a star that's had too much coffee. At its core, pun absolutely intended, a star is a massive ball of hot, glowing plasma, held together by its own gravity, and powered by the alchemy of nuclear fusion deep inside its belly. Think of it as a gigantic, self-sustaining light bulb that doesn't need to be plugged into an outlet. Instead, it generates its own electricity by smashing hydrogen nuclei together to forge helium, releasing a staggering amount of energy in the process. If you could somehow scoop out a teaspoon of the material from the center of our sun and bring it to Earth, that teaspoon would weigh about as much as a small car, roughly 5 tons, and would instantly vaporize anything it touched, turning your kitchen into a miniature supernova. So in short, a star is a self-gravitating fusion-powered furnace that lights up the universe, and it's basically the ultimate overachiever. It's hot, bright, and it never takes a day off. Stars don't just appear out of nowhere like magicians pulling rabbits from hats. They're born in vast cold clouds of gas and dust, known as molecular clouds or stellar nurseries. These clouds are the universe's version of a maternity ward, except instead of lullabies, they're filled with turbulence, shock waves, and the occasional supernova explosion that acts like a cosmic midwife, nudging clumps of matter to collapse under their own gravity. As a region within the cloud contracts, it heats up, and the pressure at its core begins to rise. When the temperature and density climb high enough, typically around 10 million Kelvin, the protons inside hydrogen atoms start to overcome their electrostatic repulsion and fuse, marking the birth of a true star. This ignition point is called the zero-age main sequence, and from that moment on, the star settles into a long, stable phase where the outward push of fusion exactly balances the inward pull of gravity, a celestial tug-of-war that can last billions of years. The majority of a star's life is spent on the main sequence, the stellar equivalent of a midlife career, where you're productive, stable, and not yet contemplating a dramatic career change. During this phase, a star fuses hydrogen into helium in its core, and the rate of this fusion determines how brightly it shines and how long it will last. Massive stars, those tipping the scales at more than about 8 times the mass of our Sun, live fast and die young, burning through their fuel in a few million years and shining with the brilliance of 1,000 suns. Conversely, low-mass stars like red dwarfs are the marathon runners of the cosmos. They sip their hydrogen fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. In fact, if you could wait long enough, you'd see a red dwarf still glowing long after the Milky Way has collided with Andromeda, and the Sun has long since turned into a white dwarf ember. Astronomers love to categorize things, and stars are no exception. The Harvard Spectral Classification System sorts stars by their surface temperature, which we can infer from the color of their light. The sequence runs O, B, A, F, G, K, M, from the hottest, bluest O-type stars. Think blazing blue-white behemoths with surface temperatures over 30,000 Kelvin, down to the coolest, reddest M-type stars, the humble red dwarfs hovering around 2,400 Kelvin. Our Sun sits comfortably as a G2V star, a yellow dwarf with a surface temperature of about 5,800 Kelvin. If you ever wondered why we call the Sun yellow, even though it looks white from space, it's because Earth's atmosphere scatters the shorter blue wavelengths, giving the Sun that familiar golden hue when it's low on the horizon. And just for fun, remember that the classification letters were originally chosen based on the strength of hydrogen lines in stellar spectra, not temperature. So the order we use today is a historical accident that stuck like gum on a shoe. When we talk about a star's size, we're really discussing its radius, and the range is mind-boggling. The smallest known stars are tiny red dwarfs like EBL-MJ 055557 AB, which is only about the size of Saturn, roughly 0.12 solar radii, yet still manages to sustain fusion in its core. On the opposite end of the spectrum, we have the gargantuan red supergiants. Take Betelgeuse, Orion's famous shoulder star. Its radius is so immense that if you placed it at the center of our solar system, its surface would swallow Mercury, Venus, Earth, and Mars, and it would stretch out past the orbit of Jupiter. In fact, if Betelgeuse were a beach ball, the Earth would be a grain of sand sitting a few meters away. Talk about feeling insignificant. And then there are the hypergiants, stars like VY Canis Majoris, which can exceed 1,500 times the Sun's radius, making them so large that light would take over 6 hours to travel from one side to the other, longer than a typical binge-watch session of your favorite show. Mass is the ultimate regulator of a star's destiny. The more mass a star packs, the stronger its gravitational squeeze, which raises the core temperature and pressure, accelerating fusion rates. This means massive stars burn through their fuel at a breakneck pace, living fast, dying young, and often ending in spectacular supernovae that can outshine entire galaxies for a brief moment. Low-mass stars, on the other hand, are the ultimate misers. Their low gravity results in cooler cores, slower fusion, and consequently, extraordinarily long lifespans. For instance, a star with just 0.08 solar masses, the minimum mass needed to sustain hydrogen fusion, can live for up to 12 trillion years. To put that in perspective, that's nearly 1,000 times the current age of the universe. So if such a star formed today, it would still be shining long after the last black hole has evaporated via Hawking radiation. Let's dive a little deeper into the fusion process that powers stars. In the proton-proton chain, which dominates in stars like our Sun, two protons, hydrogen nuclei, collide, and, after a series of steps involving positron emission and neutrino release, fuse to form deuterium, a heavy isotope of hydrogen. A third proton then joins the deuterium to create helium-3, and finally two helium-3 nuclei merge to produce helium-4, releasing two protons back into the cycle. The net result: 4 protons become one helium nucleus, 2 positrons, 2 neutrinos, and a whopping amount of energy, about 26.7 mega-electron volts per reaction. To visualize the energy output, consider that the Sun converts roughly 600 million tons of hydrogen into helium every second, releasing energy equivalent to detonating about 100 billion megaton nuclear bombs each second. If you could harness even a fraction of that power, you'd never need to worry about your electricity bill again. Though you'd also need a containment vessel capable of withstanding temperatures in the millions of degrees, which, as of now, remains a solid nope on the engineering checklist. If you're finding this stellar journey as enlightening as a supernova's flash, smash that like button and share the video with a friend who loves space. Let's spread the cosmic wonder together. When a star exhausts the hydrogen in its core, the delicate balance between gravity and radiation pressure is disrupted. The core contracts and heats up, while the outer layers expand and cool, turning the star into a red giant, or for the most massive stars, a red supergiant. In this phase, the star begins to fuse helium into heavier elements like carbon and oxygen via the triple alpha process. 3 helium nuclei, alpha particles, combining to form carbon, with a subsequent capture of another helium nucleus yielding oxygen. For stars more massive than about 8 solar masses, the fusion chain continues, progressively building neon, magnesium, silicon, and finally iron in the core. Iron is the end of the line because fusing iron consumes energy rather than releasing it. Once the core is loaded with iron, the star's internal furnace sputters out, and gravity wins the tug-of-war catastrophically. The core collapse of a massive star triggers a supernova, one of the most energetic events in the universe. As the iron core succumbs to gravity, it implodes to form either a neutron star, or, if the core is sufficiently massive, a black hole. The implosion releases a shockwave that blasts the star's outer layers into space at speeds exceeding 10% the speed of light. This explosion can briefly outshine an entire galaxy, releasing as much energy in a few seconds as the Sun will emit over its entire 10 billion year lifetime. The remnants of supernovae seed the interstellar medium with heavy elements: carbon, nitrogen, oxygen, iron, gold, uranium, essential ingredients for planets and ultimately life. In a poetic twist, the calcium in your bones and the iron in your blood were forged in the fiery hearts of long-dead stars, making us literal star stuff, as Carl Sagan famously noted. If the core collapse stops at a neutron star, the result is an object of mind-bending density, roughly the mass of our Sun compressed into a sphere only about 20 kilometers across, roughly the size of a city. A sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth, which is why standing on a neutron star's surface would feel like being crushed by the weight of a mountain range, except the mountain range is the entire planet, and you'd be flattened into a subatomic paste before you could even think, ouch. Neutron stars also spin incredibly fast, some rotating hundreds of times per second, and they emit beams of radiation from their magnetic poles. When these beams sweep across Earth, we detect them as pulsars, cosmic lighthouses that have helped astronomers test Einstein's theory of general relativity and even navigate spacecraft in the distant future. For the most massive progenitors, the core collapse continues past the neutron star stage, overcoming neutron degeneracy pressure and forming a black hole, a region of spacetime where gravity is so strong that not even light can escape. The boundary marking this point of no return is called the event horizon. If you were to fall into a black hole, please don't try this at home, you'd experience spaghettification. The intense tidal gradient would stretch you longitudinally while compressing you laterally, turning you into a thin stream of atoms before you even cross the horizon. From the outside, however, time appears to slow down dramatically as you approach the event horizon. So to an outside observer, you'd seem to freeze in time, redshifted into invisibility. Black holes come in various flavors. Stellar mass black holes, a few to tens of solar masses. Supermassive black holes, millions to billions of solar masses, lurking at the hearts of galaxies, and the elusive intermediate mass black holes that astronomers are still hunting for. The first ever image of a black hole's shadow, captured by the Event Horizon Telescope in 2019, showed the supermassive black hole at the center of galaxy M87, a glowing ring of light bending around a dark void, proving that even darkness can be breathtakingly beautiful. Not all stars end in explosive glory. Stars like our Sun, with masses up to about 8 solar masses, shed their outer layers gently, creating a beautiful planetary nebula, while leaving behind a dense core known as a white dwarf. White dwarfs are roughly Earth-sized, but contain a mass comparable to the Sun, meaning a teaspoon of white dwarf material would weigh about as much as an elephant, around 5 to 6 tons. They no longer undergo fusion. Instead, they radiate away their residual heat slowly over billions of years, cooling down to become black dwarfs, objects so cold they emit no detectable radiation. The universe isn't old enough for any black dwarfs to exist yet, so all the white dwarfs we observe are still slowly fading, like cosmic embers in a fireplace that's been burning for eons. Beyond the standard stellar life cycle, the universe hosts a menagerie of exotic objects that push the limits of our understanding. There are wolf riot stars, massive hot stars that shed their outer envelopes at incredible speeds, exposing their helium-rich cores and enriching the interstellar medium with nitrogen and carbon. Then there are Cepheid variables, stars whose brightness pulsates in a regular pattern. The period of this pulsation is directly linked to their intrinsic luminosity, making them invaluable standard candles for measuring cosmic distances. We also have magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's. So powerful that a magnetar halfway to the moon could erase the magnetic stripes on every credit card on Earth. And let's not forget blue stragglers, stars that appear younger and hotter than their peers in the old star clusters. likely because they've gained mass through stellar collisions or mass transfer from a companion, essentially the cosmic equivalent of a midlife crisis makeover. Now let's bring the discussion a little closer to home. Our Sun is a middle-aged G-type main sequence star, about 4.6 billion years old, with an expected total lifespan of roughly 10 billion years. It converts about 600 million tons of hydrogen into helium each second, releasing energy that bathes Earth in sunlight, drives photosynthesis, and keeps our planet from turning into a frozen ice ball. Solar activity, sunspots, solar flares, coronal mass ejections, create space weather that can affect satellite communications, power grids, and even produce the stunning auroras we see near the poles. If you've ever marveled at the northern lights, you're actually witnessing particles from the sun colliding with Earth's magnetic field and atmosphere. A reminder that our star is not a placid lantern, but a dynamic, sometimes temperamental, ball of plasma. Astronomers classify stars into populations based on their metallicity, the abundance of elements heavier than helium. Population 3 stars are the hypothetical first generation, formed from pristine gas, consisting almost entirely of hydrogen and helium. They are thought to have been massive, short-lived, and responsible for seeding the universe with the first heavy elements. Population 2 stars are older, metal-poor stars found in the galactic halo and globular clusters, relics of an early Milky Way. Population 1 stars, like our Sun, are younger, metal-rich, and reside primarily in the galactic disk where ongoing star formation occurs. This generational scheme helps us trace the chemical evolution of the galaxy. Each generation enriches the interstellar medium with the ashes of its predecessors, allowing the next generation to form from material that's already been pre-processed by stellar furnaces. Our knowledge of stars comes from a multi-wavelength arsenal. Optical telescopes capture the visible light we see with our eyes, revealing colors, spectra, and details like star spots. Radio telescopes pierce through dust clouds to observe cold molecular hydrogen and the emissions from pulsars and masers. Infrared observatories, like the James Webb Space Telescope, see through the dusty cocoons of stellar nurseries, revealing protostars and nascent planetary systems. Ultraviolet and X-ray satellites detect the high-energy phenomena of hot stellar coronae, supernova remnants, and the fierce winds of Wolf-Rayet stars. And let's not forget gravitational wave detectors like LIGO and Virgo, which have opened a new window by sensing the ripples in space-time produced when neutron stars or black holes merge, events that are invisible to traditional telescopes but resound loudly in the gravitational channel. Before we dive into the bonus fact, let's sprinkle in a few light-hearted nuggets to keep the mood buoyant. Did you know that if you could stand on the surface of a red supergiant like Betelgeuse, you'd experience a surface gravity only about a third of Earth's, despite the star's enormous mass? That's because its radius is so huge that the gravitational pull at its surface is diluted, kind of like trying to feel the pull of a massive beach ball from far away. Also, the fastest spinning star known, VFTS 102 in the Large Magellanic Cloud, rotates at about 1 million miles per hour at its equator, so fast that it's practically tearing itself apart, flattened into an oblate shape, and shedding material into a surrounding disk. And speaking of disks, young stars often sport protoplanetary disks where planets are born. If you could shrink our solar system to the size of a dinner plate, the protoplanetary disk around a typical newborn star would look like a sprawling pizza with toppings of dust and gas, except the toppings eventually clump together to form planets, moons, asteroids, and comets. When a star finally exhausts its nuclear fuel, its fate hinges on mass, as we've seen. Low to intermediate mass stars puff off their outer layers, creating planetary nebulae, those gorgeous glowing shells of ionized gas that look like cosmic soap bubbles. The name is a misnomer. They have nothing to do with planets, but early astronomers thought they resembled planetary disks through their telescopes. The remaining core becomes a white dwarf, slowly fading over trillions of years. High-mass stars, meanwhile, go out with a bang, a core collapse supernova that can leave behind either a neutron star or a black hole. These remnants continue to influence their surroundings. Neutron stars can spin up as pulsars, emitting beams of radiation that sweep across the universe like cosmic lighthouses, while black holes can accrete matter from nearby companions, heating it to extreme temperatures and producing powerful jets of particles that can stretch across thousands of light years. In both cases, the material expelled during the star's death enriches the interstellar medium with newly forged elements, setting the stage for the next generation of stars and planets. In essence, stars are the universe's recyclers. They take simple hydrogen and helium, cook them up into complex elements, and then scatter the results back into the cosmos, where they can become part of new worlds, living beings, and even the very atoms that make up you and me. Speaking of you and me, let's touch on why stars matter beyond their glittering beauty. The elements essential for life, carbon, nitrogen, oxygen, phosphorus, sulfur, are forged in the interiors of stars and dispersed by supernovae and stellar winds. Without the stellar alchemy that turned hydrogen into the building blocks of organic chemistry, there would be no DNA, no proteins, no water, and certainly no sentient beings contemplating the night sky. Even the energy that drives photosynthesis on Earth originates from sunlight, a product of nuclear fusion in the sun's core. So every time you take a breath, eat a bite of food, or feel the warmth of the sun on your skin, you're directly experiencing the legacy of ancient stars. In a very real sense, we are all made of stardust, and the universe's story is written in the light we see and the matter we carry. Before we wrap up, let's acknowledge that stars have been more than just physical objects for humanity. They've been musers, navigators, and myth-makers. Ancient civilizations traced constellations into the night sky, weaving stories of gods, heroes, and beasts. Orion the Hunter, Cassiopeia, the Vain Queen, the Great Bear that guided travelers. The Polynesians used the rising and setting points of specific stars to navigate vast stretches of ocean without compasses or maps, a testament to human ingenuity and the practical utility of stellar knowledge. Even today, satellite navigation systems rely on precise timing signals that are ultimately rooted in the consistent frequencies emitted by atomic clocks. Devices whose development was inspired by the need to measure time as accurately as possible, a pursuit that echoes the ancient quest to understand the regular motions of the stars. So while we now understand stars as giant fusion reactors, their cultural impact remains as luminous as ever. If you've enjoyed this deep dive into what makes a star tick, please consider subscribing to the channel for more fun, fact-filled explorations of the universe's mysteries. Hit the notification bell so you never miss a new video, and drop a comment below sharing your favorite star fact or a question you've always wondered about. Maybe we'll answer it in a future episode. Your support helps us keep bringing the wonders of science to life, one star-filled story at a time. And now, for the bonus fact. Did you know that some white dwarfs can crystallize into giant cosmic diamonds? As a white dwarf cools over billions of years, its interior carbon and oxygen can undergo a phase transition similar to water freezing into ice. But instead of forming ordinary ice, the material arranges itself into a crystalline lattice. In the coolest, oldest white dwarfs, this crystallization can create a core that's essentially a massive diamond. Think of a diamond the size of Earth, but made of carbon that's been squeezed under immense pressure and cooled to temperatures just a few thousand Kelvin. In 2004, astronomers discovered a white dwarf nicknamed Lucy, after the Beatles' song Lucy in the Sky with Diamonds, that is believed to be about 90% crystallized carbon, making it one of the largest known diamonds in the universe, weighing in at an estimated 5 billion trillion carats. So the next time you admire a sparkling gem on Earth, remember that out there in the void, nature has been crafting diamonds on a planetary scale for eons, and they're just waiting for a lucky or unlucky astronaut to stumble upon them. Though given the intense gravity and radiation of a white dwarf, you'd probably want to admire them from a safe distance.